So the original problem is given in a Macedonian contest, but let me translate to you what the statement has to say. So you're given on the input, you're given n, which can go up to n can go up to 100,000. You're given n, and then it follows by a vector of n. Let's not denote the vector, but on the input, you're given an array of degrees. So what does this mean? So you have to construct a graph such that each node has the appropriate degree. So we have 4 nodes, right? And so this node here, so the first node has a degree of 2. What does this mean? That 2 edges are coming out of this node. The second node, so this is the first node. The second node has a degree of 1. The third node has a degree of 2. And the fourth node here, they're 1 based, so that's important for later. The fourth node has a degree of 1, right? So now you have to construct a graph, but in the statement it says the graph has to have n minus 1 connections. So what does this mean? The graph has to be a tree. And all of these have to be connected. All of these, so there has to exist a path from each node to each other. So this is actually why you need to construct a tree. And you need to output at the end n minus 1 lines of u and v vertices which you connect. So what does this mean? You for example, here on the first node, you can connect the first node to here and to here. Then I see that this node has the appropriate number of degrees, right? Then of edges coming out. So this node we already satisfied that this node has 1 edge coming out of it. This node has 2, so we need to add 1 more, and this we already satisfied. So this is a tree that we can construct from this array, and the output should look like so. It doesn't matter the way you present the output. Just matters that you write out, for example, 1 2 is connected, right? 1 3 is connected. And 3 4 is connected. So I write it like this, but they are 1 3 1 1 2 1 3 4 3. They wrote on backwards, so it doesn't matter. It's bidirectional graph. It's just a simple bidirectional graph. Okay. So we know that we need to construct a tree. So this actually helps us a lot, and we know that. And if we can't construct, like in this example, we can't construct it, we say it's a problem. We just print it's a problem. So I will give you 5 seconds for you guys to go, just to pause the video right now, go solve it. The link will be in the description, and then come back and we'll solve it live. So, okay, the first observation here, other than it's a tree, we need to construct a tree and minus 1 edges, okay? The other observation is that it is like the biggest observation. It is optimal to start at the biggest edge, the edge with the greatest degree. So let me give you a better example, because this example wouldn't whoops. So this example is not that great. Okay. So let me give you with a 5 nodes example. So now here I have already sorted the array in a descending order. So it's actually very easy to find out to find this out. Is that when you start from when you start in a descending order, you need to this edge here. We need to connect to so I didn't say that the problem, if you have solved the problem, has only 500 milliseconds. So what this means is like you can only use linear or even logarithmic time, right? So what you can do here is you can start from the greatest node, and then let's only just like imagine these are the nodes here, right? So this node, I know that has to connect to 2 nodes which are with a smaller degree than him, or with an equal. So I connect, because like I can't do this because this is already not a tree. So I do this, right? And then when I come to here, right, from this node, it is possible to connect it to this node, but this makes a cycle, right? So you have to actually, so what you have to do is you have to keep track of the last node that you connected from any previous node. So if this node is if we already connect this node, we don't really want to connect it to any of these here nodes, right? So what you do is you simply take this node and connect it to the next node, to the next unconnected node. So we satisfied this node, this node remains just one edge to be connected. So let's go here. Okay, we have a pointer that like now the red pointer here moves here, right? So we can connect this node with the next node, which is not in the red pointer, right? So we connect it. Now this is satisfied, and this is satisfied. And we have created our tree. So what actually this problem just boils down into is sorting the indices, sorting the degrees by a decreasing order, keeping track of the indices, and then just going through and with just a single pointer to accelerate our process, so we don't have a quadratic solution anywhere. We can keep track. We can actually work our way through the whole tree, and we can probably we can print immediately the solutions. Just don't flash the output so many times. Yeah. Okay. Let's go and code it. Yeah. Okay. So I have here a blank piece of paper. Okay. So let's call this. I will have a vector of pair of int, because what this is going to allow us is we're always it's good to reserve the vector, if you know. So don't push back on the vector, please. Degrees, we're gonna read the degree, right? We're going to read the degree. We are going to tree at I is make pair, or we can just do this. degree and I. So put the pair of the degree and the index this degree is inputted at, right? So it's just a simple sorting here, but sorting it by the degree reversely. Okay, so we sorted the tree, the vector that is given to us. Now we have to go through the vector and we are going first to like this is the pointer and this is going to start at like 1. So first there could be an edge case if, let me see if there is an edge case. No, okay, so it's like it's 2. Okay, so n is minimum 2. So the pointer is 1 at the next element. So what we do is we start j from the pointer until the end of the tree, right? But here we can actually check immediately if the tree of I dot degrees is bigger than 0. Not dot degrees up first. Alright, so go through to the end, and as long as this is bigger than 0. Okay, so what we need here, we are going to say tree at I dot dot first, so this is the degrees minus minus, and tree at j dot first minus minus, right? And then we have to see out I tree at I dot second, so this is the index here, and tree at j dot second plus 1 because the indices are, and don't flash the output. Just an end line won't flash the output. End line as an operator will. Okay, this is fine. Now we have, I think I already have set up some test cases for us to try. Okay, so the pointer here is 1. Okay, the pointer has to extend. The pointer always extends. Okay, the pointer always extends. Now if we say here, if tree at I dot degree dot first, so maybe it would have been better to not create a pair but to create a structure, so it will be actually more understandable what we're doing. Maybe quickly we'll do that. It's not, first we have to check if it's not 0 and we're going to the next pair. Well, that's impossible to do, right? So it's a problem. Impossible is true. So we're going to have like impossible bool here. So if it's impossible, just see out problem end line and return 0. Oh, and that's why we can't flash it here. Okay. That's why we can't flash it here, but we have to create a vector of, again, I will say a pair. This is actually a vector of solutions, right? And to this vector, solutions push back, and then we can make tree dot I dot first dot second. Second is the index. Tree at j dot second. Okay, and what we have here to do is just iterate over the solutions. And see out solutions at I dot first plus 1 solutions at I dot second plus 1. So from U to V, and don't flash the output please. And at the end I'm just going to, or you can just do flush. Okay, that should work. Okay, so yeah, so do we have to create these in the grid? Like, probably we don't. Probably you understand what's the deal. So if I go run into this case, I will see that first we connect 3. We connect 3 to 2 and 3 to 1, which is correct. And then we connect 2 to 5 and 1 to 4, which is also correct. So this case passes. We're just going to test for like the problem case passes. This case also 3 3 1, so 3 3 to 1, 3 to 4. Okay, then we'll say 1 to 2, and yeah, that's it. Okay, this is satisfied. The pointer here, yes, so we started the, okay, so this should pass the cases. Okay, let's try it out. Okay, it passes the cases. Okay, yeah, and you can see it's very fast. Okay, in linear time. So this is the solution to the problem. I hope you enjoyed this wonderful little clip, and if you have any suggestions, please leave them in the comments section below. Thanks for watching.